This is a hemoglobin oxygen dissociation curve. It's a sigmoidal curve because it's an S shape. Okay, what we've got on the x-axis is the partial pressure of oxygen. So that's like saying the concentration of oxygen. And on the y-axis we've got the percentage saturation of hemoglobin with oxygen. Okay, so what does this graph show us? It shows that at low partial pressures of oxygen down here, we've got a very low percentage saturation of hemoglobin with oxygen. So where there's not a high oxygen concentration, then the hemoglobin's not got much oxygen attached to it. But this very steep rise here shows us with a small increase in partial pressure of oxygen, we actually get a rapid increase in the percentage saturation of hemoglobin with oxygen. And then it levels off a bit, so then it slows down the rate at which the hemoglobin becomes saturated with oxygen until it gets to its maximum. So it's 100% saturated, it's got its maximum oxygen it can carry. So one hemoglobin molecule is made up of 4 polypeptide chains and 4 heme groups that each have an iron. So one hemoglobin can carry 4 oxygen molecules. So this first oxygen molecule actually struggles to bind. So why does it struggle to bind? Because the polypeptide chains are very closely associated with one another. Remember that how does reactions happen? Particles and molecules are randomly colliding, so when it collides with enough energy it can bind to that heme group, and when it does that it actually changes the shape of the hemoglobin molecule, meaning that it makes it much easier for the next 2 oxygen molecules to bind. You could say at 25% saturated we've got on average one oxygen molecule per hemoglobin. At 50% we've got 2 oxygen molecules per hemoglobin, and at 100% saturated we've got 4 oxygen molecules per hemoglobin molecule. Okay, so about 25% here we've got 1 oxygen molecule bind. So why does it take so long for all of the hemoglobin molecules to have 1 oxygen molecule bound? Because hemoglobin has a low affinity. Affinity is sort of an attraction. So it has a low affinity for oxygen as polypeptides closely linked. Okay, then at this part of the graph, part 2, so this is part 1 of the graph, this part of the graph we have a sudden increase in percentage saturation. The first oxygen molecule binding changes the shape of the hemoglobin molecule, giving it a higher affinity for oxygen, meaning they can bind more easily. Okay, and then the third part of the graph here is when more oxygen is binding, and this is because it's harder again for the final oxygen molecule to bind. The reason why it's harder is not because it changes shape, it's because it just the law of chances basically. If you have a molecule of hemoglobin and 3 of its binding sites are occupied by an oxygen molecule, and you have oxygen molecules randomly colliding with that molecule of haemoglobin, what are the chances that that oxygen molecule is going to collide with that free heme group? It's going to be a lot lower. So that's why it takes a bit longer for all of the oxygen to become fully saturated, because there's less chance of a free oxygen molecule colliding with the free heme group. So we're just going to write that down. As the hemoglobin molecule becomes more saturated, it is less likely that a free oxygen molecule will collide with a free heme group. Okay, so that is why we've got this sigmoidal shape. How to describe it? Here, with a small increase in partial pressure, you get a small increase in percentage saturation. At part 2 of the graph, with a small increase in partial pressure of oxygen, you get a sudden increase in the percentage saturation of hemoglobin with oxygen. And then at the third point of the graph, with a small increase in partial pressure of oxygen, we get a very small increase in the percentage saturation of hemoglobin with oxygen, because the probability that the oxygen will collide with a free heme group, until it reaches its maximum, where all 4 heme groups are occupied by a oxygen molecule and it is fully saturated.